Plastic straws are cheap, perfectly uniform objects that we often use and casually discard without a second thought. Manufacturing this disposable tool requires a rigorous sequence of highly controlled industrial engineering steps. The process involves a physical challenge, continuously forcing liquid plastic into a hollow tube at high speeds without the walls caving in. The margin for error is zero. Even a microscopic variation in wall thickness destroys the straw's structural integrity. Producing the straw's simple profile relies on an active, high-speed negotiation with fluid dynamics. The process starts with uniform pellets of polypropylene. Manufacturers rely on this specific polymer because it yields a lightweight material that resists chemicals and is safe for contact with beverages. Before production can begin, massive silos of these pellets undergo strict preparation. They are mixed with food-safe pigments and thoroughly dried to remove all trace moisture. If moisture remains inside the polymer, the results are devastating. When the plastic hits high temperatures, the water boils and expands, creating bubbles that ruin the material's consistency. Inside the massive extruder, a rotating screw forcefully churns the raw material forward under meticulously controlled high-pressure heat. Long before it takes its final shape, the raw plastic must survive this volatile thermodynamic state. At the extruder's end, the glowing liquid is pushed through a precisely machined circular die. This forces the molten plastic into its initial continuous tube shape. As it exits the die, the material faces a structural threat. The plastic is still a hot semi-solid that naturally sags and warps under its own weight. To solve this, the soft tube passes into a vacuum sizing tank. Negative pressure pulls outward, perfectly counteracting the material's urge to cave inward. Continuous sensors monitor the diameter. If they detect a microscopic fluctuation, the system instantly adjusts vacuum pressure to maintain uniformity. This level of diameter control ensures that mass-produced straws fit securely and reliably into standard cup lids worldwide. The straw's shape is the result of an active, high-speed balancing act of atmospheric pressure. Once stabilized, the soft plastic enters long industrial water baths to harden into its final physical state. The temperature drop must be perfectly uniform. If uneven, the tube will shrink, it will violently warp, or become too brittle for use. The hardened tube then feeds into synchronized cutting machines, slicing the plastic into mathematically identical lengths every single minute. To create a flexible straw, secondary tools apply localized heat to rewarm the top portion. Specialized dies then press corrugated ridges into the wall, allowing the plastic to bend without snapping. The final structural integrity and flexibility of the straw rely entirely on this precision in timing and temperature control. High-pressure air systems rigorously blast the finished straws, ensuring no hazardous microscopic plastic dust remains from the production process. From here, automated sorting and packaging systems gather the millions of units, preparing them for global distribution while maintaining strict hygiene standards. The rigorous sequence of industrial steps required to create the straw stands in contrast to the user's casual experience with the final product. The straw's extreme affordability and reliability are direct results of highly specialized mass automation and material science. Understanding the conditions required to produce something so common offers a glimpse into the complex engineering embedded in the ordinary objects around us. The history of simple things suggests that the most complex industrial achievements are often the ones we stop noticing.